Very good. All right, let's get started. So that's my title of the talk. You registered, so you know it. Okay, so first thing I wanted to say before talking about AI or algorithms or systems or math or anything of that sort, I'd like to emphasize that humans are agents, and there are great agents and not so great agents, although they're all human, which is very important. So let's play a little bit of I don't know, like a thought play or like a game, right? So if you were the owner of a firm or managing something important as a group, and you were trying to hire an employee, a human employee, which is also an agent, an important agent in our society, what kind of characteristics would you like the human to have? If you care about the company that you're managing. Yeah, go ahead. Efficient. Oh, okay. Maybe was that because of the slide leaking? But that's great. I'm very happy regardless. A lot of common sense. Yeah, kind of smart or reasonably intelligent in some way. Truthful, so responsible, trustworthy. Yep. So I guess we need to pause. So kudos. So smart in some sense, broad sense. Truthful is responsible, trustworthy, truthful, ethical. People skills. Oh, fantastic. This is something that definitely did not leak, I thought. So that's great. So this is legit. This is a wonderful audience. So team player, collaborative, and things of that sort. Okay, fantastic. So why should we not care about AI agents at least having this kind of a skill set? At least a subset, right? Maybe someone's inefficient to start with, but probably it should be performant or smart in whatever it's doing. Or maybe it's not so smart, but super efficient, right? I don't know why one would care about an AI agent to do work for you, which is being employed by you, while being not efficient, not smart, not responsible, and not a team player. You don't want that. But that's not where the conversation of agentic AI has prominently been around. There's always some threads about this happening prominently too. But I'd just like to highlight this so that we have some perspective, because we are forming, we're not building the matrix like the movie, we're building something for our society, right? Okay. Okay, another thing, yeah, I'd like to have some more conversation on is, how many of you think that the word AI or the usage of the word AI in our current discourse suggests that AI is part of the usage of our word agentic AI? So is AI part of agentic AI, or is agentic AI part of AI, or are these two the same things? How many of you think AI is part of agentic AI? Okay, it's okay to not have an opinion. Yeah, okay, so there's one. Oh, great. This is all ill-defined, hence the discourse, hence the confusion, right? There's no abstract definition of AI yet, and there's a discourse that's still happening, but there's a usage of the word AI that's happening. Similarly, how many of you think agentic AI is part of AI? Okay, that's a lot more. That seems kind of reasonable. Seems like it. Okay. Or it could just be the same and just a play of words, like overloading of terminology and creating more buzz. It's not completely the same, at least that's good. So they're not selling the idea of some snake oil to us. There's something little new about agentic AI, right? At the same time, the whole emphasis here is this usage of the word AI everywhere, hence the big buzz about AI, and hence, since it's being used in many contexts, there's an overloaded usage of the same word to mean many things. So when there's confusion, it's good to create an abstraction of it, right? Kind of formalize things a little bit, or at least go towards formalizing things. So there's a need for abstraction in this kind of agentic AI/AI discourse. Okay, so that you avoid the circular reasoning fallacy, right? Okay, so I'd like to take a use case of something that's happening quite actively all around us. Some of you might have already heard about this. Okay, this is a survey that I'm really interested in. So how many of you have already heard of OpenClaw, Claudebot, or yeah, so this is quite an AI savvy audience in here. So we can take this use case and try to create a little bit of abstraction. There are many ways to create an abstraction. One is you could do some math, you could write some code, or you could create a flowchart, or you could use a lot of boxes. So this is abstraction with boxes that we're doing here. Okay. All right. So for those who've not heard of OpenClaw or Claudebot, this is an AI-based service which could also be called a platform. There's some servitization happening here, where it allows you as a human to engage with popular communication channels for input-output, such as Slack, WhatsApp, Telegram, depending on where you are and how you operate in your region. And all that human interaction is taken in the form of text or speech from these platforms that you anyway interact with. And there is some sort of a gateway service which kind of redirects the context and message that you provided the system in order to either trigger some usage of some tools or some already known or inbuilt skill or some sort of code that's already encoded internally. So a tool could be something of the sort of, so if you did a walkthrough, I walk into the system and I say into my WhatsApp message to say to the OpenClaw, hey, open up my Gmail and read this email from Emily. I just want to be sure I'm coming to the right building to give the talk, right? So that's a walkthrough interaction. So that goes in and it gets somehow routed into my email and I'm opening a tool. So there's a decision maker, which is the agent runtime, as they call it in their architecture, which does some of this decision making of what kind of tool needs to be opened and in what order and how do they interact with each other and how is the information gathered and so that it's finally presented to the human. There's some memory for these things to happen because it's keeping a track of things that you immediately asked and some of the recent interactions you've had in the past so that it builds a bit of a persona for your personality as it keeps interacting with you in the future. And then at the same time, it does what you asked for. It'll open the email, all that stuff will work. But in order to make some decisions of that sort, there may be answers that are coming out not from just the gateway that is routing your request or an agent runtime, which is opening up some existing tools, but it could also happen directly from an LLM, a local LLM. An LLM is a large language model, and a local LLM would mean that it should either be a small language model or a medium language model, or something needs to be very efficient for a large language model to be a locally hosted LLM on your phone or something of that sort. Or it could directly interact with an LLM on the cloud, right? So the cloud could be a GPT or something of the sort of Claude or Mistral or DeepSeek and so on and so forth. And all of that will bring you the answer, okay? So there's some abstraction of what an agentic AI platform of the kind of OpenClaw CloudBot does. At the same time, I'd like to build a bigger box of world models, because language models is one class of models trained predominantly from language data and other kind of documents. But you could have a world model or like a multimodal language model or maybe not a language model or a world model of how people interact in the world or look at the world, talk to the world, and that's a broader class of models of which LLMs are a smaller subset. There's very recent activity happening on world models around the world and of course in MBZI as well, right here in Abu Dhabi. Okay, so what do we take from here? There's an environment of input-output, some agents, AI and human. Human is not visible in the picture, but it's there. And a plan is being built by the agent runtime as to what tools need to be opened up and what actions need to be made. And you always reason with either a big brain or a small brain or like this brain that's kind of spread across between the agent runtime and your large language model. Any questions on this kind of boxes and flowchart of what OpenCloud is? Okay, great. So some takeaways are there's some sort of perception or sensory connection to the world through, of course, WhatsApp. It could be more broader or generic. Some sort of reasoning and planning that the LLM, the whole system is doing, that includes LLMs. And you're executing and obtaining feedback. You're executing actions and obtaining feedback. So that's an example of an agentic AI system that the world is currently looking at, okay? All right, so let's keep moving. Yeah, please. Yes. So why it is revolutionary is a bit of a viral kind of phenomenon, so I may not comment too much on that. So anything can go viral for various reasons. But these all fall under a similar, okay, one thing that made things a little more, I wouldn't say revolutionary, but popular is because the open source nature of it. I mean, you could literally instantiate an OpenClaw on your phone and talk into WhatsApp or Telegram or whichever system you use. So that's making it very popular. And there's been a lot of surveys and discourse on what an agentic AI platform would be, where AI and tools that we currently have interact together. There's not been like some real world instantiations of what people have been talking about and strategizing in documents and surveys, right? So that's a real world deployment that's working very well to do what it's promising. That's another thing that made it very popular. It seemed a little magical that you have this kind of real world form factor where you see it as opposed to reading about it in a survey. This is just my viewpoints. I don't know, did you say Claude Co-work or Claude? I've not heard about Cloud Co-work, right? I don't have to, but I will look into it. I'm very interested. And it's an ongoing. Yes, exactly. That's what I meant when I said I don't have to, but I'm very happy to look at it. Okay, very cool. Any more questions? Okay. Yeah, please. Very good. That's my actually next question in the slide. It's this part of the agent runtime, the AI, the artificial part, and this LLM interaction or this world model interaction. These two are AI models for different reasons. This is some sort of a multi-agent model in an environment where decisions are being made and you're seeing actions and rewards and more sequential decisions are being made. Reasoning and planning is being made, which is classical AI box of, or like a treasure trove of problems of how to reason and plan. And similarly, the large language models and world models are part of AI. In here, that's the box. There is parts of it that are evolving, which is here. You're making sequential decisions as you interact, as a human interacts. There's pre-trained models that are being used here. The ones in the cloud are pre-trained, so you're not training. It's not your duty to train it when you, as a user, but you still get the benefit of it because they're pre-trained. Or you could fine-tune them, which is ta-da, kind of the topic of the course. Well, not the course, of the talk. Yes. Yeah, please. Yeah, that's very critical because I was looking some YouTube videos on show me a demo of OpenClaw before I asked my student to do it. It seemed very scary the way they were kind of treating this as magical, but their description was along the lines of there is this OpenClaw that can look into all the data in your computer, read all your emails, and do everything that you do not want a computer to do. So there's OpenClaw currently is a treasure trove of bugs for security and privacy attackers, right? So that needs to be fixed. And security and privacy is a field in itself, just like AI is. So there's a whole stack of sub-problems of how to do inference with LLMs with privacy, like where you just ask a question, you don't train anything. How do you tune or fine-tune an LLM with privacy and so on and so forth? How do you prevent jailbreaking an LLM, which is some sort of a social maneuvering that people do when they say, call us and say, hey, I'm your bank, when they're not, for instance, if it was a spam. All that kind of thing is jailbreaking, where you're kind of figuring out a prompt where the LLM is so brittle that it does something or leaks something. So there's so many problems in there, but it's a very important point. Okay, yeah, last question, then we keep moving. Seems there's something interesting about this slide. Yeah. Sure, yeah, there's a question about labels such as input, output, and gateway for different parts of the system, and there's no label for the bottom left and also the right in some sense. So what would I call it? I would call it the following. So that's reasoning and planning. It's figuring out based on your question, like a human asked natural language question that you either talk or type, and what needs to be done, what tools need to be open, or no tools need to be open, or we just ask the LLM or do something else, figuring out a plan of actions. That's this part. This is traditional large models or ML models of any sort. So we can call this a data science box because a model doesn't have to be a large language model. So the AI that I'm trying to emphasize was the previous question from the gentleman there, as he pointed. So the AI is a mix of this and this box predominantly, because there is some sort of a RL or a reasoning or planning or some sort of a search that's happening here, just some sort of intelligent action making or decision making, and so is the traditional LLMs, which are all over the news and in our face, right? So that's AI too. Okay, so we did a nice exercise with boxes, so we have a better abstraction than just calling agent or agentic AI or what we don't know what we're referring to, right? No, it's more clear. Then there's just an instantiation. There's one instance of what agentic AI is. There are different variations of this, obviously. Okay, let's keep moving in the interest of time. So what is missing in all of this? Humans. There's no humans in this picture. But where do humans fit in? Humans fit in the training of all the large language models. Most human data has been taken into there, sometimes with some infringement and hopefully many times without an infringement. Humans are the people talking into these channels, and humans are also intelligent beings as a result of a lot of evolution. They're amazing. So that's human in the loop. Humans are using all these tools and services, such as booking.com, where you book a ticket, or your Gmail. So all of this is a human society. So humans are prominent. So we've been talking about perception, reasoning, executing actions and rewards, which is primarily from an AI standpoint. But humans bring in a lot of important characteristics to this interaction. Okay. So maybe a generic abstraction could be of this sort. This is from a white paper by Erickson. I think that got cut, or maybe it's too blanked out, which is a reasonable abstraction of what we saw in an instantiation of an agentic AI system, which is OpenClaw in the previous slide. But there's some generic, boxing of paradigms. There's machine learning, the traditional where you learn models. There's machine reasoning, which is also quite important. And there's always some interaction between these two. And so on and so forth. Okay, you get models here, you infer some knowledge, you plan. So the reasoning models reason and plan and perform actions. Look at reward and so on and so forth. There's a bit of an overlap in these two circles in the way people refer to these things. But to those that have, say, never heard of this, for example, this is good to have these kind of circles or boxes as opposed to none. Okay. All right. Okay, human viewpoint. Humans are important. Right, we talked about these four. So we want agents to be the following as well. For instance, privacy or security aspects fall under responsible or trustworthy characteristic of an agent. Efficiency is super important. These are large language models. Sometimes it's a few trillion parameters, so they won't fit in your phone unless you do something about efficiency. Performant in the sense that it's doing something well, like it's being evaluated to do something well. It's performing well. Collaborator, they can work together, right? So agents work together. And eventually, we'd like to have a system, we're not here yet, where it's welfare maximizing. So we have a society of agents, and you're trying to maximize the welfare of agents. Sometimes these societal agents could be strategic, and maybe there's no 0-1 game, sometimes there's a zero-sum game, right? So maximizing the welfare of society where agents have preferences and perform actions is also important. We've not got there yet. Okay. Okay, now let's start opening the hood of the car, or like in this case, and let's get inside an agent. So to set some context, we've not got inside the agent here yet, but this is outside the agent before we get inside it, right? So this is, for example, from MBZI. We've done many of these things where we've taken a public LLM from the cloud, such as, say, Llama, and we kind of fine-tune it, which means you fine-tune it like it kind of literally says, to adapt to your specific knowledge or your documents or your domain of expertise. Like broadly speaking, here I mean fine-tune it to say become very reasonable at answering medical Q&A of the kind that you typically search in Google sometimes before you head to the doctor, right? I have a fever in this range, and I'm twitching my left eye, and I feel shaky. That's something you sometimes search. So you want to have an agent answer things. And of course, it being responsible and all of that is very important. But that's the process of fine-tuning, where you provided some documents and or some body of knowledge, and it gets a little more adept at what you're doing. And then you have, again, an outside of the agent, right? This is the hood of the agent, right? So you have an interface where you have, say, a web LLM, which is a fine-tuned PubMed Q&A kind of an agent for public medical questions. Okay, so what happens inside an agent, right? Inside an agent, this is what's happening, because you're starting with a very large model. You're coming down to an agent that is specialized for you, and hence the process of getting there is called fine-tuning. And you want it to be extremely efficient, right? Because you don't want to be as much work as training the large language model in the first place, which takes millions of dollars by these large organizations. Okay, to get some context from a methodological standpoint, in data science or like in ML, data collection is an important process. Pre-training or pre-processing so that you generate a very large model is an important process. And right now this is happening typically by centralized or powerful authorities or companies. This is a world that we moved into in the last few years. And then you fine-tune those large models so that you get smaller models, which are your agents, that run either locally on your device or somewhere in the cloud on your behalf. So, and then you infer, you kind of predict and talk and interact with these agents. It could be an inference with the pre-trained model, a large model, or your fine-tuned agent. And you retrieve answers and do things around this, okay? So we're focusing more on the fine-tuning aspect of how an agent gets generated, okay, from a large model. One thing that I'd like to note about this centralized and participatory aspect of things is the follows. We've used the word privacy even before privacy was formally defined. It's a social word. So is welfare. It's a socially used English word before someone defined welfare in markets and did a lot of work and won a few Nobel Prizes in the economics area, right? Or we talked about things like security or safety. Now we're talking about same things because as humans we care for our agents to have those characteristics like we mentioned. There is something that we've not talked about, but it's already there in our society, and that's quite important, which is this notion of liberty, okay? Liberty is, there's no formal definition for this yet, but it's all around us. When there's privacy that you care about in an informal sense, and you formalized it, there's fields built on top of privacy. There are Turing Awards won on privacy, right? What is liberty? Just from social perspective, there's no formal definition, right? Liberty is the following. Liberty, as it suggests, is using your freedom to use as many resources as possible in this context, okay? Pre-LLM era, there was a little bit of some sort of a skewed balance, but not complete imbalance. LLMs were generated as a result of the some agents in the society using their liberty to max out the usage of their resources. Is there something good or bad about this? Can someone say something negative about what's the issue of some parties using so much liberty of using resources to generate an AI agent, which is a large language model? Do you know what could go wrong? For instance, copyright, super important. Yeah, some reliability issues and hallucination and factual. Yeah, please. Yes, so it's not very reliable currently, right? The state of this, although there are platforms for it. There's a dream about agents working in a utopian way on a platform. Platforms are being figured out, but these things have not been figured out yet. There's some work happening. So yeah, very true. Another thing, there could be less participatory say of other parties. The agent that's training this and using millions of dollars has almost say in how this, as long as they're trying to stay legal somehow, right? Or the time period of how this model is being built. And that leads to unfairness downstream, or like lack of participatory activity by other agents. So this is something I'd like to definitely flag. That's happening all around us, so we need to also think about this as a concern and act on it. I'm not saying we stop training large language models. That's not the takeaway. Okay, so now we looked at the UI of an agent and what fine-tuning is and the methodology. We talked about these things. Now let's just open up one way of fine-tuning. I'll show you multiple things and different works we've done. I'll be happy to share these slides or place them online after the talk in the coming days. The link on the first slide below my name is where you'll see papers that came as a result of this work on which the slides have been built on top of. We've had 3 ICLR papers. There are like ML people in here that are being covered in this talk, and there's other papers that came out as well around this. Okay, so parameter efficient fine-tuning, because models are big and you want to be efficient about fine-tuning them. So what's the problem here, right? The setup is as follows. You have a very large language model, which is the one on the left, which has pre-trained weights, because this was a result of spending many millions of dollars and going through a lot of documents and training a huge model. And when you fine-tune them on your local data set, because you have very local data, like the PubMed Q&A, so that you can ask, have an agent that does good on public medical Q&A questions, for instance, you want to update this model. You want to create some gradient and some drift on this model, which is your delta W, so that you have an update. And this is typically an iterative process, but nevertheless, you want to figure out eventually a trajectory where you have an updated model, okay? So that's the delta W here. And the rest stays the same. The model takes data in, something comes out, and decisions are made, and predictions happen, and prompts are written. The answers to your prompts come out. Okay, nothing of that sort is changed, right? So in order to be able to update, say, a 3 trillion parameter model, you don't want to fine tune it where you make 3 trillion parameter updates and learn them optimally. It'll cost you as much or even more amount of money than the original training that costed in the first place. GPUs can be costly when you're taking them to the max. Okay, what you want to do is an idea from, I mean, most scientists stand on the shoulders of giants, so this is very classic. This is just standard undergrad matrix multiplication or factorization in some sense, but just like classical, beautiful 1950s style and post-1950s, but pre-modern, current era linear algebra, right? You're just writing your large matrix as a product of two small matrices, which the community calls as adapters, right? So low rank adapters. So now you have n by r times r by d, as opposed to a full n by d matrix, right? So n by r plus r by d is a smaller set of parameters. Basically, you have smaller set of parameters to deal with when you're fine-tuning than the entire matrix in itself. Okay, so this is LoRa with thousands of citations, right, from a few years back. Okay, but that hasn't solved everything. There's been some more architectural fixes before some bigger problems started showing up. Some architectural fixes include the ones such as this, which is quite interesting. This has happened in October 2024, for instance. There are many variants of this, where you take the LoRa, and what you saw here is exactly the LoRa you saw in the previous slide. And then what you do is you insert another small matrix in the middle. So now you have even tiny parameters. You're multiplying three matrices. It's like r by r, even small square matrix. So that's even more parameter efficiency. All that is good. This is great. You're reducing the number of parameters that you're supposed to train. You're just reducing the count, which is a great start, and already that shows great promise. But then it opens up new questions now, because the current methodology of how these adapters are trained are as follows. You initialize, okay, in this particular case, the only thing that is trained, like I said, a small one, which means your pre-trained matrix, this is like your chat GPT that you pre-trained, initialized with, or your Claude. And these adapters are all frozen. Good thing is the pre-train has a lot of intelligence built into it, because it's a result of the humanity and like some companies training very large models. That's nice. But these two are frozen currently to be random initialization, okay? And you're fixing them. That's random initialization, which is nothing to do with your data, okay? Or the kind of questions that humans ask. The only thing that's trained based on your data is a small matrix. That's where the fine-tuning knowledge is being embedded into the system as a whole. So that opens questions. Is this optimal? Is this doing very well? And is the room for improvement very less? So can we stop here? Or is there something that needs to be done? This is far from being suboptimal in getting the best solution when you train this way, okay? So what does optimal mean, or what is great, okay? So this is some more work that focused on this, but in the setting where you don't have that small little matrix in the middle, right? So it's again the classic original LoRa setting, but it's answering a very nicely phrased question. How do we initialize our adapters, anything that's unfrozen, that I start training and fine tune on my data? Initialization seems to be a great important point to first figure out. Yeah. Yeah. Yeah, so there's no one answer for it, because I can give some anecdotes, right? For instance, yeah, so, oh yeah, the question from host is, if you have a large language model that you use as your pre-trained initialization, say how large is that traditionally, and how small are the corresponding adapters? Okay, so I can just give anecdotes, some magic numbers, because the whole gamut of models, right? So These kind of papers typically work on experiments because they're not inside the huge companies, coming mostly from academia, or work on order of 7 to 9 billion to 20 to 30 billion parameters in a large model, which is a version of the pre-trained model, which itself is not extremely large, but still sizably large. State-of-the-art large language models, like in terms of size, the biggest ones of a order of like 3 to 5 trillion parameters, if you really can handle that to start with before you pre-train them, fine-tune them. And now coming to adapters, so say it's a matter of what method you use, how well it performs, because there's a trade-off. But again, some more magic numbers, you can get down to an order of few million as opposed to a few tens of million parameters as opposed to the few billion or trillion parameters you started with. Okay, does that give some magic numbers? Okay, yeah, please. Mm-hmm. Sure. They might respond differently to pharmaceuticals than cell bodies. And then can I still adjust that with this factor? Where we can throw everything away and stuff. Okay, something very philosophical. None of these methods are a crystal ball. There's room for improvement. None of these are crystal ball. They're human loop and you're interacting them, nudging them. But yes, now less philosophical. Benchmarking in a way that matters to your domain on which you're training them. Maybe it's a gynecological set of ailments that you're fine-tuning with. That's a different domain than, I don't know, male health in some other fashion, right? So it's up to you how you create the benchmark. This is what's happening around us. The performances being reported in the real world are empirical. There's no theorems and lemmas in performance. There's theorems and lemmas on other aspects of the training, but not in performance. So it's as good as your benchmark. That's somewhat real world practical information. So the goal is not to cheat ourselves into thinking that we're creating an agent that's very good because we kind of falsified a benchmark. That's not the point. The point is it's as good as a reasonably constructed benchmark. Right? Yeah. Okay. Yeah, please. Yeah, yeah. Yes. Exactly. So if it was assumed to be, which is not, if you assume it to be the linear world, that's the beginning of your weight matrix, and that's where you factorize it, then the Cauchy-Young theorem is as good as you can do, like under some norm. But this is not the case. That's where you see the gaps in optimality. And we've designed non-LoRa adapters called ABA adapters, for instance, which is part of ICLR. We'll get to that as well, which clearly shows how this does better than just doing an SVD. And also the solution here is not SVD yet. If I give you the matrix and ask that, then it is, but that's not what's used in the traditional LoRa. Yeah, yes. You are reweighting the prompt, you said, or rewriting? Rewritten prompt, okay, and then? Oh, okay. Yeah, the difference is the pre-written prompt would get an answer that's as good that the LLM could answer with pre-trained weights, right? But if you're asking things that is not its speciality, or if it's not enough compression happened to give you the right specificity of like a good answer as a human, as you're reading the answer, that's the reason for why you want to fine tune. Secondly, you want to do it efficiently because you can't pre-train because most of the world is not as powerful as this large company. Yeah. Okay, let's keep moving in the interest of time. Okay. So in terms of answering how to initialize, it seems like the first thing to figure out, like if you're writing code for this, you download a pre-trained model and then you want to update it. You want to update your model. First thing you want to write in your code is download and initialize my weights that I'd like to update my adapters. But that has not been figured out, and there's been hundreds of papers and thousands of citations and LoRa work, right? So that's an important problem. So this was the first paper that figured out what's a good way to initialize, and their scheme is as follows. They show an equivalent gradient. So what does it mean to be optimal now? We've not defined that. So something optimal is as follows. If I had billions of dollars or millions of dollars, and instead of fine-tuning, I kind of update the entire trillions of weights instead of the adapters, and I get the gradient of these updates, right? If I can mimic that full tuning, full pre-training kind of a training process, and how good this could do, and if I could mimic those gradients, that's optimality up to some notion of closeness. So I want to mimic the full fine-tuning gradient as closely as possible, and that's as big as the trillions of parameters. So these authors showed that there's an equivalent gradient, say G tilde, which lies in the subspace of gradients for your individual adapters, which you use to update your parameters. And it lies in a linear subspace of these matrices. So it's like a linear subspace. That G tilde is just an equivalent notion, but you need to figure out the right GA and GB and the right A and B to initialize so that your transformation will take you to the optimal gradient. So G tilde, the optimal gradient, is a subset of this subspace. And it's as close as possible to your full fine-tuning gradient in the Frobenius norm. This was the LoRa Pro result, okay, of how you initialize fine-tuning optimally and your optimalities in terms of mimicking full training gradient. Okay, but this has not been answered for this beautiful architecture with the smaller matrix in the middle, where W naught is your pre-trained model, B and A are frozen. You want to figure this out. So how do you initialize B and A in this architecture optimally? That's our first of a series of papers. This is Laura Silver Bullet. These are our students at MBZUI when they did this work. They're right now at EPFL. Okay, and this is a faculty at MBZUI. I as well am. This was a postdoc who's now a faculty at MBZUI. Alexei Tumanov is a systems for ML for systems guy at Georgia Tech. Okay, all right, so this is Laura Silver Bullet. And we show the similar theory, but done derived in a different way that is specific to this, where we have, again, a similar thing, where we show that if you initialize B and A the way we prescribe it, then you will just need to use a similar transformation where you'll be in the right subspace. So that if you're doing full fine-tuning, the black line, this is the optimal gradient that you would get if you used all the trillion parameters and millions of dollars. But if you did the adapter updates, you want to be as close as possible within that subspace, within the Frobenius norm. But if you initialize these things wrong, it's as good as garbage in, garbage out for the initialization. You'll end up in a wrong subspace. There's no escape there. You're fairly far off from the optimal full fine-tuning gradient. Okay. So 3 words here: initialization, equivalence, a map to the right subspace, a transformation that maps the right subspace, like having a functional form of that, and then optimality, which is closeness in Frobenius norm. So these are the objects in here. I've seen this fair proportion of STEM, science, tech, engineering, math kind of people, backgrounds in here, and quant. So the objects are full fine-tuning gradient. You want to mimic this, but you don't have the money to do that. There is a LoRa XS or a LoRa Pro style gradient of that small R by R matrix, which is an update you can make. If you can make a wrong update or a good update, that's the gradient, that's the other object. We want to have optimality. We want to figure out some transformation, G tilde, from however you initialize A and B, and you do a usual gradient update using PyTorch, TensorFlow, your usual backprop of how neural networks are trained. And you do this mapping. There's a small scalar parameter. We'll talk about it. It'll vanish later. You do this mapping, and then we show that that's where you need to search for the optimal gradient update. And you need to, it's also a matter of right initialization. Otherwise, it's just a functional form with 4 unknowns, right? Of which currently 3 things remain unknown, and people are just feeding gradients into this and not even mapping it this way, right? That causes being far from optimal. Okay, so I said this is the functional form. This happens to be a more exact version for that architecture. It has a similar functional form. There's a 6 scalar. There is your gradient update for R with PyTorch or TensorFlow, and some matrices of this kind, right, which have this form. Good thing, people don't like inverses, and we're talking of billions of parameters or models, like at least millions of parameters. The good thing is, I'll skip the proof for that, but I'll say there's no fancy math in here, machinery here yet. The way we show this functional form is through some traditional calculus and chain rule kind of stuff, right? Just done carefully. Okay, there's no fancy math. You could always interpret it in a fancier way, but that's later on. Okay, so skipping the proof. So we show a computational way for using an exact instantiation of that equivalent transformation, which I'll talk about. So that's the first thing that we saw. This is a problem. This is needed because your original W0 is not optimal for your new data set. Hence, you wanted to fine tune. Otherwise, your B and A would just be identity matrices, which is not the case. It's still in the previous method when this was not done outside of LoRa silver bullet. It has a lot of hyperparameters, which kind of vanish in our case, as you will see very soon. The computational thing that we do is as follows. This is driven by lemmas that kind of direct us to do this. Is the follows. So it's kind of also speaks a lot about how many samples are needed to do a good initialization, empirically speaking. This is a practical computational aspect. We take our fine-tuning data set, which could be a large data set, but we uniformly sample just a handful of samples using current benchmarks on current benchmarks, right? For whatever data set we're doing. We compute a full fine-tuning update or just the matrix for the weights. And then we perform a low rank approximation, like our math friend in here has said, using SVD. And we use that to initialize the B, A, and R in our transformation as follows. B and A happen to be orthonormal. And as you remember, in our transformation, there was a B transpose B inverse and A transpose A inverse, which was optimal form. But that vanishes because it's orthonormal. So there's no B and A. The S for other internal reasons also vanishes. So what does that mean? That means you don't have to do anything different, but something very simple, which is get an estimator for your full fine-tuning gradient on a very small set of uniformly sampled points from your fine-tuning data set, perform its SVD, and then update these matrices as we suggested, and most things will vanish, and you'll just continue to do your training, where whatever remains will influence the direction to be optimal in that notion. And then we also show that this kind of update, we are able to show like a descent direction. We are able to show some convergence with, of course, a lot of assumptions. And we see this in practice. This is what I said. So you just set the initialization by giving the approximate updates, and all the problems we had previously are solved in one shot and guaranteed theoretically, which everything's in green. This is just a small subset of improvements, like to one of Horst's reasonable question on some order of parameters of large. For say, if you started with a llama 7 billion parameter pre-trained model, I mean, you could scale this up more, for sure. A traditional LoRa will say, if you use a rank 32, you have about 83 million parameters, so tens of millions of parameters, as opposed to 7 billion that you need to update. But it may not perform optimally. But if you did full fine-tuning, it performs to some extent, and that's what you do. But then if you did lower access, you're reducing your parameters to like a 0.23 million, like a smaller set of parameters, fewer thousands of parameters. But the game is, and so does LoRa Silver Bullet. It follows the same architecture as LoRa Pro or LoRa Access. So these are similar. It reduces as small as the BAR kind of an architecture. But the key is the gain is in performance, right? So we perform much, much better than the previous ones. This is to someone's question, I think your question on, I have some specific data set in my real world, I want to fine tune it. How good is it going to do? It's as good as your benchmarking, right? Okay. So is traditional ML, pre-LLM as well, in modern deep learning, unless you're proving generalization bounds for like a smaller set of models. You would see these kind of empirical loss reduction curves where if you did something other than LoRa Silver Bullet, like the LoRa Access, right from the beginning, you would see in the beginning epochs, you would see a clear difference. This is already going in the wrong subspace. There's no escape for it. You could run it forever. You will not see a double descent. You will see a double descent just within this subspace, but you'll never jump to the other subspace that matters. That's very clear. And you will see with LoRa Silverbullet way, way better all the time, okay? And it's very easy to implement and use. The code is there. You can always reach out to me for the Git link. GitHub links is in the paper too. It's quite modular. So you take whatever pre-trained model you want and then call our initialization, our Silverbullet initialization. The rest stays the same. You don't have to rewire or do something underlying with the GPU or like some low-level code. You just use PyTorch or whatever interface is as is and call our library for this part. Okay, any questions there? And checking time as well. Okay, sunset is very important. All right, so any questions? And also nudge me on, I'm getting towards the end anyway. The trade-off in terms of performance or? Oh, yeah. So this is this magic number of 100 I mentioned, right? It's actually, this is what I'm trying to say. It's these experiments shine again and again, shine some light on the importance of data selection for your fine tuning. Because you may have a fine tuning data set that's about a library of how to read radiology images of a specific kind for an ailment. But the importance of selecting the right samples and the sample complexity for doing this kind of thing, the sample complexity seems to be low, empirically suggesting there's no bounds on the sample complexity. Also, there is an importance of the value of selecting the right data. What if my 100 samples, if I play that adversarial kind of game and like the devil's advocate, if I selected the wrong 100 samples, it's quite easy to do when you have millions of samples, just even from uniform sampling. What's the effect of it? These are kind of important. I mean, the 100 samples seems to be fine in our simulations, however we do it. So it means it's not a very robust decision point in terms of how sensitive the downstream things would happen. But it also says something about this phenomena. What is happening, right? Because this pre-trained model is trained on entire internet in some sense. And you're fine-tuning them using very few samples. It's kind of quite a magical phenomena. Yeah. Okay. All right. So can someone nudge me on the timing of when I should conclude? Because I shared the flavor of what I'm doing, for instance, but there's many more things. Yeah. 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 Without the mix. Right. No, good point. That's exactly the topic of my next slide. Not necessarily federated, but also collaborative. Federated is referring to the same thing, where you have multiple experts and agents, and you have multiple agents in a box, that kind of question. So this is for solving problems where all your agents are already miscalibrated and suboptimal the way you train them. So fixing that aspect, and you're kind of building on the collaborative or private nature of things. Yeah, it's a relevant question. Yeah, anyone can always nudge me to stop in the next coming 5-10 minutes, because many people, and there may be other logistics involved with the iftar. Okay, all right, so collaborative. Now you have too many agents coming from all sources. How do you put them in a box so that they're kind of doing something that's increasing consensus and like better decision making or better intelligence? This was the world of federated learning pre-LLM. Right now, we're in the world of federated learning post-LLMs, right? Where you download some pre-trained model and you upload some agents and you want to figure out how to gather them, right? Broadly speaking. This is again the status quo. There is a whole gamut of papers again, of course, smaller than the LoRa number of papers. But there's again something very fundamental that just went missing. Even more fundamental than the previous one, because that had more mathematical machinery. This has almost no math, very, very basic high school math, but something went missing. Maybe at the pace at which we're going, I guess, and the buzz that we're building, we're kind of sometimes kind of not slowing down and looking at things carefully, right? What went missing is the follows. In traditional FL, pre-LLM, it makes sense to train models and create different agents and then kind of aggregate them or average them. That seems to do well, and that's a reasonable decision to do under assumptions. But here, you cannot just train LoRa adapters separately and average them, okay? That will never be the same as the average of the products, like, right? So you want to product them and you get the model, you want to average those models. But as soon as you product them, you're back in the trillion parameter space. You will lose the efficiency of LoRa. But you cannot average them separately because a product of sums is not the same as sum of products. It's for that reason. That went missing. So we had to course correct this in our paper, and that ended up in ACL, because it's more applied ML, this particular one, in order to be able to do federated, efficient, and down the lane, of course, private LLM fine-tuning, where you can fine-tune with LoRa-style architectures, with parameter-efficient fine-tuning, and also federate them. So there's that. It's a very simple protocol. And we already see huge improvements with other federated methods for this reason of wrong averaging of such huge matrices, right? So we are better on the, this is like for privacy, this is like with privacy, differential privacy put into our training, but even with that differential privacy and different popular benchmarks for arithmetic tasks, for common sense reasoning tasks and natural language understanding tasks and so forth, which are popular benchmarks, we get a better efficiency performance trade-off than current methods. Kind of looks like it's kind of Pareto optimal relatively to this, but we don't know where the real Pareto is. Okay, and then our FedSB is already deployed by Argonne National Lab, and we're running a global cohort where I'm actually working on engaging MBZUI and MIT also to participate as part of a federated silver bullet, like very well engineered deployment of this algorithm that builds on LoRa silver bullet and also does the right averaging. It's part of right now part of the AppFL open source framework by Argonne, which lets you do federated fine tuning across the globe, across countries. And right now, AppFL focuses on enabling AI for science, but FedSB is not specific to AI for science. It can enable any kind of AI federated fine tuning. Okay, this is the last couple slides. Now we are moving very quick. There's some snapshots. This is another ICLR paper from this year, where we throw LoRa out and we introduce ABBA. Because LoRa, you're still restricted to the low rank degrees of freedom. You're searching for low rank matrices. In ABBA, we use a simple trick, which is you can have a product of LoRa adapters, but that product is a Hadamard product, and that will always make sure you're at least greater than the rank of what you currently have. So you're able to model an unknown delta update through your fine tuning, which could be potentially of higher rank than what low rank would, what typical LoRa would allow. And we see that in many kind of experiments with structured matrices that we perform better than traditional LoRa with using ABBA adapters. And then the last two slides is on our work in DP Fusion for LLMs, again in ICLR this year, which is about privacy. So how do you infer and make sure you don't leak PII information when you're using your documents or prompts? So you can sanitize your prompts, or you could sanitize the output of an LLM so that it doesn't leak PIIs and have formal privacy guarantees. And this is based on differential privacy. At the same time, I'd like to conclude on some things here. Which is this thing that I keep showing in many of my talks, which is this is how our telephone network was operating a few decades back. If you were supposed to make an international phone call, that's what was happening. There were people kind of frantically working to try to find your slot to call someone, and they were connecting wires right across the network, right? This is how they're trying to do this. You're trying to book a slot to make a phone call. We don't do this. We take communication for granted, and it happens seamlessly. That doesn't mean there's no tech involved. Of course, there's a lot of high-tech deployment and a lot of algorithms were figured out. Right now, where are we living? In the current decade, we're living in a world where, of course, there was an ICT revolution. Seamless communication has been achieved, a lot of good networking. Where we live in a world of data silos. There's so much data that's not being mixed together, and there's a lack of collaboration. So we're heading towards a world actively through work such as these, where we are opening up seamless collaboration by default, where you don't think how agents work together, it just happens seamlessly. Just like you don't think how Google.com loads when you load it, all the web tech is happening seamlessly. That's the world we're moving towards, and that's where I'd like to close it. Thank you. Yeah, thank you, Horst.
Mark, you're going to go around and have a microphone. We'll take a few more questions. The sun is still up, so please be patient and ask questions. Yeah. Yes, back there. There will be a microphone coming. Please wait for the microphone so our online listeners can capture questions.
Yeah. So my question is really simple. So actually, so in order to apply your research on our models in our company, we just have to download the codes and just have to train them and actually check the outcome, like this. So that's what I wanted to know.
Oh, yeah. So the beauty of your company would be the domain knowledge that you have within your company, as long as it's in a digital form that can be fed into these kind of LLMs. Say if it was a vision language model, you should be having some vision and some language data. If it's a traditional language model, you'd have some language data or structured data or tables. And if it is something that's unique to your company in some sense, as opposed to like public information, right? So you're trying to build a fine-tuned model that is a specialization for your company to create a chatbot that performs way better as an agent. So that's the process. And I have a startup myself, Agentoids LLC, where I've been doing this with a very large law firm, for instance. That's our first client, where we're creating a very specialized agent.
Yeah. So all of the links can be found in the articles.
On the papers,
yeah. Okay, great.
Or you can reach out to me.
Very useful. Yeah, thank you.
Yes, right. Thank you.
Thank you. Yes, there in the second row, in the first row.
Hi, you've obviously done a lot of research on benchmarking, and from your recent experience, do you think fine-tuning is actually necessary or not really? Because from the results that you showed, they seem to be, the standard stock model seem to be very performant anyways.
Optimal fine-tuning or closer to optimal fine-tuning is necessary if you want to keep pushing the limits of how well you do and pushing the limits of efficiency.
So what are some of those use cases where you would recommend fine-tuning?
For instance, there are companies where you could have very specialized edge device hardware. For instance, this is just an example from my head. This is real, right? Where you cannot even load a model and train even a single round. So you cannot fine tune even using not optimal or like some old LoRa. You still cannot do that because these edge devices at the most, if they're doing ML, they traditionally can do inference and they're still fighting for speed of inference efficiency without training just prediction. So now you know where the world is at. And now you know why you need efficiency and performance. This is the reality of the world. But you could also be a large company, not like in the siloed with a small edge device. It'd still be a large company, but then right now, agents that are specialized to do everything in the world are not specialized enough to do the thing that you care about. That's the reality of it. Or we'd be in a world that's been taken over by agents, and OpenClaw would be the platform of some variant of that where this magic is happening. It's not happening, which means there's a lot of room for doing things more optimally. And there are other ways of fine-tuning. This is just one way, which we also work on. Yeah, cool.
Great talk, by the way. Thank you. I like your metaphor of comparing AI agents to humans. And if you run a company, you have the choice. You can hire a lot of generalists or you can hire specialists. The specialists, they all do a certain task and they contribute to, let's say they write a document together. And one is really good at security, they focus on the security aspect. Somebody is really good at databases and they focus on, and so on. Right. And overall, the document gets much better. You're actually proposing that we turn everybody into a generalist by fine-tuning the model and making the model know about security, know about this, and then you grow the model. That's in contrast with goals that we have to run it on phones, as you said a couple of times. So there you need quantization and you need to compress. Of course. So that makes it all very complex. You want to make the model bigger, and quantization wants to make it smaller.
Yeah. So
in companies, you have people
there, though.
Yeah, and the second thing you talk about a lot is collaboration. So could this be solved by just a swarm of agents collaborating and contributing parts of the solution, rather than try to fine-tune generic models?
Yeah, very, very enlightening questions, relevant questions. The first thing, I kind of disagree with the order you mentioned because it's a bit of a converse. This is not a way to go from a large model to a more general model. This is a way, fine-tuning in general is a way to go from a very large model, a general model, to a more specialized model. That's the order of things, which is what all of these methods are. On the other thing on having many, many agents, this is the problem, right? So having too many agents, I mean, you could have consensus if these agents are reasonable. There's right now, most of these agents are disproportionately working, not in consensus and in synergy. Secondly, we don't know one agent, how we could do multiple tasks. And similarly, we don't know how many agents could do a new task. Because otherwise, your best agent would be
But
the
humans
best
have the
task.
same problem. Like, how do we solve that as humans?
We work with each other. Agents are, we
Exactly,
don't have a way to do
yes.
it. Yes, hence we
Yeah.
need
So
collaborative
this
methods.
sounds like a very interesting research project for me.
Yeah, absolutely. Yes, for sure. Yeah, I could give a quick example. For instance, you could have agents that are great on portfolio optimization, for instance. Say you have those agents, and say they're proprietary to a very powerful entity. And now you put that financial hedging kind of agents in a box so that someone could use it in some form. And then you could have an agent that's doing sports betting, for instance. Sports betting is not exactly portfolio optimization like traditional markets. It's a little different, which means you need to have these agents work together to do that specialized task. This is kind of an analogy of there is no exact mapping of all tasks to one's best agent. Those don't exist, which means current agents that are doing some things need to work together to do your new thing better.